to heck, we can move to this one. We're not expert in Atwood, so type 4 or 5, whatever. Same question. Let's imagine that we're given alpha, we're given beta, we're given MA, we're given MB, we're not given the mass of the putty. We're given mu K, we're given mu S, which suggests that there is friction between A and the ramp and B and the ramp. Let's imagine that we're given the direction of motion, which is that B is going to go down the inclined plane and A is going to go up the inclined plane. Let's again consider the fact that we start from rest. A is going to move by a distance d on the inclined plane, and B is going to go down by the same distance d down the inclined plane. Okay, so exactly the same problem. We know all those quantities, and we're looking for the velocity, which by now we know is the same for both in magnitude, after both systems move by a distance d along the inclined plane. I strongly suggest that you redo this problem on your own, but this time, instead of considering or going after the velocity of both objects after they displace themselves by distance d along the inclined plane, that you ask a similar question about their velocity, but after both objects have moved by a vertical distance d. Then you will see the difference in your PEG. All right. Again, we have two massive systems, therefore we're going to have two sets of energy terms for each. Let's pick a coordinate system. This time, let's pick our 2 points as usual, 1 and 2, 1 and 2. But, you know, for the fun of it, let's pick a coordinate system at 2 instead of 1. Since we just did 1, then we get to practice both. As we apply energy conservation law, we have the sum of all the terms, plus, again, we have more than one system, therefore we have to add the kinetic energy term for both. We have no spring, so we're just going to consider PEG to the gravity. And then same on the other side. This would be for state 1, state 1, state 2, state 2. All right. Let's tackle that little bugger here. Let's do a free body diagram on object A and a quick free body diagram on object B. What are we going to have? Let's start with A. What are the forces acting on A as it goes from state 1 to state 2? All right, the usual suspect. MAG, the normal force, and A, the tension. We know this tension is the same as the other tension because we're going to use Newton's third law and the property of the massless body. And we have friction. We know it's Fk because the system is moving, since we're calculating the velocity. We know that A is going up, therefore Fk is going down. Bang. All right. As we go after B, we're going to realize same amount of forces. MPG, NB, tension. And this time, object B is going down, therefore Fk is up in the same direction as the tension. And they are different. So let's call it Fka and Fkb. Because remember that Fk's functional form is mu Kn, therefore the n will be specific to each of those objects, as you've seen earlier with Newton. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8 terms. Again, let's go through one after the other. We don't have to worry about the work term due to the weight, because we're going to include the PEG. We don't have to worry about the work done by NB, neither the one by NA, because both normal forces are perpendicular to the displacement. The displacement for B is in this direction, and the displacement for A is in that direction. All right. We've seen earlier that if we calculate the work done by the tension on A, we're going to get the exact same value in magnitude as the work done by the tension on B, except with a negative sign. So as we add those two work terms, they're going to disappear. Out. So really, only two. So, as we apply the functional form of work, for both cases, could you give me the relationship between FKA and its own displacement dr? What is the relationship between those two vectors? Look at your free body diagram, and let's investigate the dot product first. Is FKA parallel to dr? Is it perpendicular to dr? If it's parallel, is it in the same direction or is it in opposite direction? Yeah, opposite direction. Therefore, what does it imply on the outcome of the dot product? Excellent. Thank you, Tyson. Thank you, Nuka. Thank you, John. So this will be negative. And FKA is mu K and A. Next one. What is the relationship between FKB and the displacement dr of B? Obviously the same, opposite. Therefore, we're going to pick up the same negative sign. But this one will be mu K and B dr. Okay? We know mu K is a constant, NB is a constant, N is a constant, so we can take it out. And we have negative mu K and A times D. And here, we're going to have negative mu K and B times D. No problem. Now we need to go after NA and NB. Because remember on the link, on the test link, he asks you to work down and express all the work term in terms of given quantities only. So we have to express NA and NB. That means that for that part, we have to go back to Newton. But we've done this before. If we look at your free body diagram, let's say A, which direction would you like to pick to apply Newton's second law in order to express NA in terms of given quantities only? Which axis, which free body diagram would you like to pick? For example, we pick Y. Where would you like to align, or how do you want to align your Y-axis on the free body diagram of A? Yeah, excellent. Thank you, Anaka. We want to pick this. Why do we want to pick this again? Because if we do the sum of the forces in the Y direction, it will not include the tension, which we know nothing about. It will not include FKA, which obviously we don't know either. But it will only include NA, which is what we're looking for, and the component of the weight. Bing! So, as you apply Newton's second law to only the Y direction, so that's the only one that will be useful for us, then we're going to pick up NA minus MAG cosine, and this will be 0. Hence, NA is nothing else but MAG cosine alpha. So the work term can be expressed now as MAG cosine alpha and D. Okay? And that rings a bell. We recognize that term from Newton. Let's do the same thing on B. Let's pick our axis such that Y is along NB. X, anywhere, we don't care. And let's only do the sum of forces in the Y direction, which involves NB. Right away, we know the right hand side is 0, and all we have for the Y component of the forces is NB minus MBG cosine beta. So again, same as Newton, this will give us MBG cosine beta. Now we can express the work term for the friction on B entirely in terms of given quantities. Now we can plug numbers if you wanted to. All right? And we ensure that both terms are negative, as they should be, because friction has a tendency of create negative work, which is why we quote-unquote lose energy. All right, let's put those two little buggers back into our equation. Work done by the friction acting on A plus work done due to friction acting on B. Plus, we have two massive terms. Therefore, we need a kinetic energy for both. 1/2 ma VA squared plus the one for B, 1/2 mb VB squared. Now let's add a potential energy term for each of those two little guys. Again, we have no spring, so we don't have to carry out the PS. We can do it right from the start, and we only have to consider PG. So we have MA, G, HA, and then MB, G, HB. Let's duplicate, the last four terms. Oh yeah. Yeah, some people may decide at this stage to rotate their paper to a landscape situation. Or use solid paper, whatever works. Okay, and now let's pick our two states. We call them 1 and 2. 1, 2. So 1 for this guy, 1 for this guy, 1 for this guy, 1 for this guy, 2, 2, 2, 2. All right. Okay, let's go through the first kinematic term. Is object A moving when it is located at state 1? Yeah. We will start from rest as usual. My bad. So if we start from rest. Excellent. My bad, I forgot. yeah. Usually it's simpler to just start from rest so that we can use all the key term. But it is possible that we may have given an initial velocity on A, for example, which obviously would be the same for B initially, say a little initial velocity down the inclined plane. So that if MB is much, much bigger than MA, the kinetic of the system would be for A to go initially down the inclined plane and then back up. The only difference is just to keep your kinetic term on the left-hand side. All right, so what about the kinetic term for B at state 1? Is object B moving at state 1? Same reason, they're both at rest. We know that VA and VB in magnitude are the same, so if one is 0, the other one is 0. Good. Now let's look at our free body diagram. What is the vertical position of object A at state 1? Is it on its x-axis or not? Nope. Excellent. Is it below or is it above? It's below this time, so we know it's going to be negative. All right, let's draw it. This is HA1. As you draw it, you now realize, a nice little right angle triangle. Therefore, can you give me the functional form of HA in terms of D and alpha? As you identify the right angle triangle, HA represents the opposite sign of your right angle triangle that you can express easily in terms of the hypotenuse and the angle alpha. Can you tell me how? You've done this a zillion of times. We are trying to figure out the functional form of HA1, this, which is the vertical displacement. But we also realize that this vertical position is one side of a right angle triangle that we're familiar with, right? Yeah, excellent. Sine. Perfect. And we know, again, it's negative, therefore, negative MAG D sine alpha. Perfect. Let's look at B at state 1. This is B at state 1. Oh, how do we get the sign? Look at the green right angle triangle. This is the hypotenuse, D, and we're looking for H. H is the opposite to the angle. Therefore, it's sine. Right? Yeah. In this class, it's all about right angle triangle. So train your brain to always identify a right angle triangle. That's all the geometry you need. That's it. Excellent. Excellent. Oh my God. So now let's look at B. As B is in state 1, is it located on its own x-axis or not? Nope. It's obviously above. It's above by this distance. That's our HP1. Same thing. Identify the rest of the triangle. This is the distance D. That's your right angle triangle. And that's your angle beta. Therefore, not only HP1 is positive, but is it in terms of sine or cosine with respect to D and beta? Which one? Sine or cosine? Excellent. Yeah, sine again. So this time, positive. MPG sine beta. Perfect. Kinetic terms. Well, obviously, we're looking for that velocity, so we need to keep it. 1/2 ma. V, we realize also, same as before, that the string doesn't stretch, therefore the magnitude of the velocity A is the same as the magnitude of the velocity B, so we can drop the subscript. Now, potential term. Where is object A located at position 2 with respect to the x-axis? Or is object A at position 2 on its own x-axis? Yeah, you're right on it. Easy. B. As we look at position 2 for B, right here, is object B located on its own x-axis when you reach position 2? Yeah, same as before. Excellent. So as you can see by now, if you decide to pick the origin of your coordinate system at either of those 2 points that you've selected, then all your PE will be 0 on one side of the equation. If you select to put the x-axis on state 2, all the PEG will be 0 on state 2. If you decide to put the origin at state 1, all the PE at state 1 will be 0. It's only if you decide to put your datum or the x-axis as at neither 1 and 2, which was the case for the vertical loop or the case for the pendulum, that you're going to have PE term on both sides of the equation. Perfect. That's it. So really 1, 2, 3, 4, 5, 6 term. Let's start for V. It's a little bit messy, but not too bad. GD is everywhere, so let's take it out. MB sine beta. Then we have a MA sine alpha. Then we have mu K. Let's take it out because it's common to both. And we have an MB cosine beta. And then an MA cosine alpha. Yeah, and I close my parentheses. And that's it. And then I have that stupid going to F2. Poof. And of course, I can factor the V out. Therefore, I need to divide by the total inertia. MA plus MP. Done. Easy. And again, as you look at all the terms, you realize, hey, very similar to the acceleration. Yes, it is. The only difference is this factor, and that factor. Because it comes from the usual v squared, v naught squared, which is 0 for us, plus 2ad. This is the extra 2, the extra d, and the extra square root. Nice. Again, when you finish the problem with Atwood, always check every one of your term. You know that what goes in a denominator is a total inertia. Therefore, since you have two massive systems, that's total m. Always plus. Cannot be negative. It's the total inertia. And then as you look at each term on the numerator, you know that the term that will obviously cause the whole thing to go in this direction is the weight of B. The bigger the weight of B, or the bigger the mass of B, the bigger the acceleration or the velocity. So this one should be the positive term. That's the one that will feed the velocity of the acceleration. Sure enough, bang, it's positive. Now you know that if A is on the other side, as you increase the weight of A or the mass of A, is going to tend to decrease the velocity or the acceleration, right? It's counteractive. So it's going to have a negative sign. Sure enough, bang, negative sign. And as when you apply Newton, you know that the friction term is always positive. Since it's being distributed to both terms, they're both negative. I'm sorry, negative. Because the friction will tend to slow down the system. So always check your sign at the end. If it doesn't follow common sense, you know, oh, okay. Either I goof in the algebra or I goof somewhere in my terms, but usually PG is the source of the problem. Okay, does that make sense?